I'm going to talk about the work we've been doing using satellite remote sensing for water quality assessments in Minnesota and how we're automating that in a high performance computing environment. This is part one of a two-part presentation. The second part will be about linking water quality variables to landscape stressors. So we do, we take the data that's regularly collected by citizen volunteers. At the same time, we have satellites regularly collecting imagery. So what we do is we find good, clear imagery from a late summer index period, be a time of algal maximum, kind of the dog days of summer, usually August, September. And we take the clear images, link that back to water clarity within a few days of the image, build a statistical model of that relationship. We apply that model to all the lakes in an image. We do that for enough images to come up with the water clarity for the whole state. Using that methodology, so far we've completed 9 statewide assessments since 1975. There's over 10,000 lakes assessed in each of these assessments. And we've used it for analysis of spatial and temporal trends and causal factors, and I will be talking about that in the second part of the presentation. About in 2001, we made all of the data that we had available in a lake browser. It's an online resource, kind of like Google Earth, Google Maps, and you can get a lot of information about your lakes. Very popular with over thousands of visitors every month. And recently we migrated that to an ArcGIS server, and we updated with 2010 and 2015 water clarity data. So that was to maintain a 5-year interval. The 5-year interval has been great. It's been real popular. But if we really want to improve lake and fisheries ecological management, we need more water quality variables more often. And that's where we're going with these new satellite systems with Landsat 8 and Sentinel 2. We have higher spatial, spectral, radiometric, and temporal resolution. So there's a lot more data these days, a lot better data, and it provides a new opportunity to look at not only things that water clarity, but also the factors that control water clarity, things like chlorophyll, color dissolved organic matter, the brown stuff in water, in the picture down here, and then things like suspended material as well, not algal stuff. So all these different characteristics have different signatures in the data, and the number of the spectral bands determines how well they can measure the different variables. So if we look at these variables, if we look at just water with a lot of other stuff in it, you're gonna have a peak at about 550, the blue one here. Once you get chlorophyll in the water, or algae in the water, you're gonna have this peak at 705. And then you're gonna have this absorption trough at about 670, and then another absorption trough at about 620. The 620 absorption trough is due to cyanobacteria, or there's a phycocyanin due to cyanobacteria in the water. Once you have a lot of CDOM, if you have nothing else in the water but CDOM, you're just going to have hardly any signal at all for a satellite, and that effect is very strong in the short wavelength. It's very absorbing, and it decreases as it goes longer. So if you look at it, compare the yellow one, which is a chlorophyll dominated water with also a lot of CDOM, you can see how it pulls the shorter wavelengths down compared to the green one here. So it kind of pulls the whole spectra down here. If you have a lot of sediment, you're not going to have the absorption factors due to the photosynthesis. So you're just going to be more across the whole there, like this brown one here, but not high. This is high CDOM and a lot of sediment in it. We look at the spectral bands. With Landsat, we're missing this red edge. That's a very key band for chlorophyll measurements. And so without that, we are not able to measure chlorophyll very well. So we basically say it's good for the CDOM, and it's really good for water clarity. It works just as well as the other satellites for that. Sentinel 2 has this band, and the Sentinel 3, which is for larger lakes, has the phycocyanin band at 620. We have all this new data, trying to make good use of it. We've been exploring cloud-based image processing, Google Earth Engine. Using that, we've basically kind of perfected some of our methodologies and getting it ready for for routine monitoring, we're building that code onto our Minnesota supercomputing high performance computing environment, and make an opportunity for a near real-time water quality monitoring system. So the imagery is being regularly collected, goes to the different data stations, ground stations. Then we have machine-to-machine access right into Minnesota Supercomputing Institute. We can download all the imagery, go into the different processing, those are remote sensing procedures, which we've been doing manually before. And we're basically kind of modify those to work in an automated environment. One of the key differences here is the atmospheric correction, removing all the effects from the atmosphere and the sun angles, and to normalize the imagery so that we can apply models. Instead of for each individual image, we can apply it to an atmospherically corrected imagery that works for a lot of images. So with that, the other thing we've been doing is the water mass, getting rid of the affected pixels like aquatic vegetation areas. We have mixed pixels around the terrestrial areas, the shoreline and such, and then the cloud and haze mask is very important. So once we're left with just open water clear pixels, we can apply our water quality models, and we do that. Then we have basically we can output the data in either pixel or REST or aggregate that data at the polygon level or lake level data, make it available for people. So with our automated system, here's our May through October for 2019, just kind of give an idea of the clear imagery available. What we have is quite a few images that are available for the statewide, where before we had one assessment every 5 years from a late summer. Now we can do the whole season and kind of pick up a lot of different characters that are missing. So what you notice here is the blue one's a lot more data points. That's due to the overlap area of the imagery. And then these are kind of in between those overlaps. There are fewer data points in those areas. Can also have plenty of data at the monthly level as well for most areas. I think there's a little bit of a missing spot in September, but other than that, we have some good data sets throughout the summer for the open water season for water quality measurements. So with that, we can make some maps. So right now our approach is to make monthly mosaics, and at the pixel level, and then also have at the polygon level, have every measurement that's collected actually in a database, but that can be compiled with whatever season you would like for your different research opportunities. For those that are not familiar with Minnesota, it's a very unique landscape here. We have quite a transition, 7 different ecoregions. We have up in northern Minnesota, more like the Paul Bunyan land here. We have northern Minnesota wetlands and northern lakes and forests, which is mostly lakes, wetlands, and forests. And then we have the agricultural ecoregions to the west and to the south. And then we have the transition zone, the north central hardwood forest, which is a mixture of both agricultural and forest and wetlands. With this unique landscape, we also have some very neat, unique waters. We have very optically complex waters. Okay, so we look at the data. This is from our current data that's on our lake browser. And these are the data points that are available. We have looking at spatial and temporal analysis of water clarity. And this is at the ecoregion level. So when we look at the lakes up in this area, the northern lakes of forest and the northern Minnesota wetlands, some of the best water clarity in the state, even though visually the northern Minnesota wetlands is kind of overwhelmed by the Lake of the Woods and the upper and lower red, because those are lower water clarity lakes, but there's lots of smaller ones that you can see. Then the north central hardwood forest, the transition zone, would be the next best water clarity. And then once you get to the agriculture, we have lower water clarity in there. If we look at trends, we have found that 16.2% of the lakes had linear trends of changes of greater than 10 TSI units, trophic state index units. And this is equivalent to a doubling or halving of algal biomass, or a doubling or halving of a Secchi disk measurement. 5.5 of those were increasing water clarity, and 10.7 were decreasing water clarity, greater than 10 TSI units. So it's kind of going in the wrong direction for those. Took a little bit smaller of a slice, 5 to 10 TSI units, so not quite doubling or halving, but still a significant change. 22.6% had linear trends of this magnitude, 9.2% increased water clarity, and then 13.4 decreased water clarity. So when you take a look at the pie charts here, we can see a lot of the agricultural ecoregions have a lot more of the red and the orange. So lakes that are decreasing water clarity than improving. If you look in the north central hardwood forest, more of a mixture, kind of going both ways. And then one thing that was kind of surprising to me was the northern lakes of forest, which is kind of a more pristine, more oleotrophic waters. And there's a lot more, especially in the orange category, that were decreasing. So there's something going on there. Part of the reason for the analysis looking at the landscape features is to figure out what's going on. And so to start with that, I looked at temperature and precipitation, and found the more recent time periods a little bit more wild for the temperature, the blue line here. And for the temperature has been increasing and staying warmer for these long period of time. So it's about 3% increase, which easily could be contributing to differences in chlorophyll levels, because algae likes warm conditions. And that is a finding from a Nature paper, where they also use Landsat data to look at trends in 86 lakes, I think, and basically found significant changes in lots of them, and attributed, they didn't really have enough data to actually attribute to any one factor. There were multiple factors going on, but the ones that didn't change were the ones that were in areas where the lake water temperature didn't increase. We can also map CDOM. So far we've mapped CDOM for 2 different time periods, 2015 and 2016. And so here's our 2015 and then 2016. And what we found was there was a significant difference between the two in some areas. And this was true in our fieldwork and then also in our satellite remote sensing. One big factor for these big differences was precipitation events. 2015 was a very normal year, whereas 2016 was lots of big storms, and made our fieldwork actually kind of more difficult that year. So lots of wet conditions. So with these wet conditions, with more water coming in the system, you're either you can push the CDOM that's sitting in the wetlands nearby into the lake systems and through the system. So if we look at where the high CDOM lakes are distributed throughout the state, a lot of them are up here in the northern Minnesota wetlands, and then the northern lakes and forest ecoregion. A lot more lakes in this here, so you just have to the scale. The difference in scale is quite huge for the number of count of those water bodies. If we look at change, what we found is that lakes in ecoregion and agricultural ecoregions tend to actually decrease, or 7% of the lakes actually decreased CDOM greater than 3 440s. So basically, I think we attributed that to more dilution because there's not as much organic carbon in the watershed, whereas in the northern lakes and forests, there's a huge increase with 31 and 28% increases in these ecoregions, and 30% of the lakes of greater than 3 A440, showing A440. So there's some things going on, and that would be due to these massive wetland complexes that are where all the vegetation is just cooking. It's kind of like a tea bag in water, and as we get these pulses of rain, it pushes it into the lakes and through the chains, and you can see some dramatic changes. Okay, with all that, we're hoping for an enhanced lake browser coming out later either this year or early next year. Basically, instead of having data every I'd say 5 years at late summer, we're going to have monthly data so we can start to kind of explore that type of data. So it should be a nice data set to have. Also exploring this, using this data in other areas, South Dakota, Wisconsin, Iowa, and then looking at some of the southern states. In the southern U.S., there's a lot fewer clouds, and so there's a lot more time steps for clear imagery, and so you can get some pretty dynamic animations of what's going on in the water quality with that. And, with that, I will leave my acknowledgements and